Hi, everyone. Today we're going to be talking about exponential growth and decay models, and we're going to be looking at some applications. But first, I just want to go over again what exponential growth and decay is. So, when we were talking about graphing exponential functions, we said that if the b value or the absolute value of the b value was greater than 1, then we would have an exponential growth function, and it would look something like this. So, it would be increasing from left to right. If we had an exponential decay function, we said that the b value or the absolute value of the b value would be somewhere in between 0 and 1. And the graph is generally going to look like this, where it's decreasing from left to right. So we'll look at a couple of examples of how to identify exponential growth or decay from the model, and then we'll actually write some out and then calculate some examples. So for the first one, if we look at this function, y is equal to 8,000 times 1.15 raised to the x. In our notes last week, we said that the value that's in front of the number with the exponent is the a value, and the number with the exponent is the b value. So in this case, if our b value is 1.15, and we were to take the absolute value of that, that's going to be obviously greater than 1. So this is going to represent an exponential growth function. If we look at example 2, it looks like our a value here is 20 and our b value here is 0.75. So if b is 0.75, or we can write that as 3/4, the absolute value of that is somewhere in between 0 and 1, which would represent an exponential decay function. And then example 3, y is equal to 15 times 1/2 raised to the x. A is 15, b would be 1/2. So absolute value of 1/2 is in between 0 and 1, so this would also represent a decay function. And with these ones, we just have to be a little bit careful because in this f of x is equal to 6 times 5/2 raised to the x. A is 6, b would be 5/2. But if you think about what 5/2 is, that's really 2.5. So absolute value of 2.5 would be greater than 1. So this is going to be representing an exponential growth function. So just because you see a fraction here, again, just be careful because sometimes it could be a growth function and not a decay function. All right, so let's look at some application type problems. We'll look at kind of more of these as the unit goes on, but we'll kind of just start with some basic ones today. So the first thing I want to talk about is the actual model. And we generally say that the exponential growth model looks like A is equal to P times the quantity of 1 plus R raised to the T. And a good way to determine if it's a growth model is that this value in this quantity should always be greater than 1, because we should always be adding something on to 1 to make it bigger than that. So what do these variables stand for? Well, P, we'll start here, this P is going to be the initial or the principal amount. Or basically, that's the amount that you're starting with. R is actually going to be our rate. And we always want to write our rate as a decimal. T is going to be time. And 1 plus R is representing our growth rate. Or in this case, that's really representing our B value of our function. And then A is going to be whatever the amount is that we're ending up with after we calculate all of this stuff. So let's look at an example. Compounding interest problems are generally kind of the most common problems that you'll see of these types of problems. So in this one, it's saying that you deposit $1,500 in an account that pays 2.3% interest compounded yearly. We want to know how much money would you have in 2 years if you didn't deposit any more money. So we'll kind of go through and define what each one of these things mean, and then we'll kind of put it together and answer the question. So what was the initial amount invested? Well, the initial amount invested would be this 1,500. What is the growth rate? Well, the growth rate is 2.3%, but written as a decimal. Remember that when we're writing percentages written as decimals, we move the decimal place over to the left 2 places. So if I move it over 2 places, that would actually give me 0.023. The growth factor is going to be this rate plus 1. So my growth factor here is going to be 1 plus 0.023, which is going to be 1.023. And this is going to be representing our B value. So if I want to write an exponential model to represent the scenario, I'm basically taking these 3 things that I just found here, and I'm going to go ahead and write the model. So I'm going to write this as A is equal to, I'm going to plug in my P of 1,500 times the growth rate. That's the 1 plus R. So I'm going to make sure to write this as the 1.023 raised to the T. And the model is always going to be written in terms of T. So we want to leave that as a variable. If it's asking you to write a model, it should look something like this with a variable of T. So then let's answer the question. Well, it's asking us how much money we would have in 2 years. So our T here is going to be 2. So I can use the model that I just wrote in the last part of this question, and I'm going to go ahead and say, okay, well, my A is going to be equal to 1,500 times 1.023 raised to the second power, because that's where my T is going to come in, my 2 years right here. And then at this point, I can just use my calculator or use Desmos to evaluate what this is going to be. So 1,500 times 1.023 raised to the second power. And if I didn't deposit any more money in the bank in that time period, this is going to be the amount that's left over or that's ending after 2 years. So it's going to be about $1,569 and about 79 cents. All right. So I know this says you try, but I do want to go through this one because this one's a little bit different because it's not talking about money. But it's telling us a tree 3 feet tall grows 8% each year. We want to know how tall the tree will be at the end of 14 years. So my P, or my initial value here, is actually going to be the 3 because that's the height that my tree is starting at. So my P is 3. My R is going to be 8%, but again, I want to write that as a decimal, so it's going to be 0.08. If I move the decimal place over to the left 2 places, 1 plus R is going to be 1 plus 0.8, which is going to be 1.08. And just using these 3 pieces of information, my model is going to be A is equal to 3 times 1.08 raised to the T power. And what I want to know is what is going to be the height of the tree after 14 years. So this is going to be my T. So now that I have my model right now, I can answer the question. So A is going to be equal to 3 times 1.08 raised to the 14 power. I'll go ahead and use my calculator. So it looks like it's about 8.8 feet. So the tree will be about 8.8 feet tall after 14 years. Okay, so those are just some examples of some exponential growth models, meaning that the value is going to be increasing. There are also exponential decay models where the elements are going to be kind of the same as what we talked about, but the only difference is that the stuff or our B value is actually going to be a little bit different here. So our decay function model is going to start off the same. It's still going to be A is equal to P. We're going to open up a set of parentheses, but in here, what we're going to say is we're going to say that this value is actually going to be 1 minus R raised to the T. because we know that in a decay function model, our b value is less than 1 or in between 0 and 1. So whatever our rate is, we want to take away from 1, which will get us that value somewhere in between 0 and 1. And p is still going to be our principal, our initial. The rate is still r, and we're still writing that as a decimal. T is still time. And 1 minus r is actually now going to be our decay rate, which again is representing our b value. So let's look at a couple of examples. So depreciation is a big decay model type problem that you'll generally see. And depreciation just means, like, if you think about car depreciation, that means that your car is lessening in value over time. So we buy a new car for $22,500. The car depreciates at a rate of 7% per year. We want to know what the car will be worth after 5 years. So our initial amount that we paid for our car is going to be $22,500. Our decay rate is 7%. But again, we want to write that as a decimal, so it's going to be 0.07. Our decay factor is going to be 1 minus this 0.7, which is actually going to give us 0.93, which again, this value should be less than 1. And I want to write a model to represent the scenario. So A is going to be equal to 22,500, which is my P. Drop in my 0.93 raised to the T power. And again, my model is going to have this T as an exponent, as a variable. And then I want to answer the question. Well, I want to know what the car is going to be worth after 5 years. So here's my T. So A is going to be equal to 22,500 times 0.93 raised to the 5th power, because that's the amount of time that I'm looking at here. And that looks like after 5 years, my car is going to be worth around $15,652 and about 99 cents. Okay, so we'll look at one more example together. So a butterfly population is decreasing at a rate. So decreasing, this should indicate that this should be some sort of decay model at a rate of 0.082% per year. There are currently about 100,000 butterflies in the population. We want to know how many butterflies will there be after 250 years. So this 100,000 is our current population, or our initial or starting value. Our rate is 0.82%, which again, we want to move our decimal place over to the left 2 places. So it's going to give us 0.0082. 1 minus 0.0082 is going to give us 0.9918, which is going to be representing our b value. And then our model is going to be A is equal to 100,000 times 0.9918 raised to the T. And then I want to know what the population is going to be after 250 years, so my T is going to be 250. So using this model, I'm going to answer my question. So A is going to be equal to 100,000 times 0.9918 raised to the 250. And then this is going to be my population after about 250 years. And in my calculator, I am going to get a decimal here, but remember that we're talking about butterflies, so we don't want to have a decimal of a butterfly, so I would just round to the nearest whole number. So this number that you're getting at the end should definitely be less than the number that you're starting with, which this definitely is. 12,000 is less than 100,000. So I'm just going to write a little sentence here. So after 250 years, the population of butterflies will be around 12,765. All right, so now I'm going to have you guys try some on your own, and let me know if you have any questions.